bubbles in some type of homemade container. I'm not sure. I stole this from the cupboard. Some child probably made it for my wife. But anyway, we have a container of bubbles, and I need to kind of stand back from you guys here. I want you to think about something with these bubbles. That is that it's hard to grab the wand. Oh my goodness. All right. So I want you to think about something as a bubble is blown. That was a pretty good one. It's kind of neat, right? You maybe want to come up and grab it. Okay, I know I'm having all the fun. I can't like walk around and get close to you here, otherwise I'd be blowing it in your face. But think about something. Now that I mention it, wouldn't it be true that the way that the radius is changing, if you will, the size of the radius, it would definitely be true, just from a geometric standpoint, that that has everything to do with the volume of the bubble, right? As the radius goes, so does the volume. Now, if you're like, you're getting a little geometric on me. Well, there's a formula for the volume of a sphere. It's 4/3 pi r cubed. Don't worry about that too much, but do realize that the volume of this bubble, as it goes, or I should say, as the radius goes, so does the volume. That was interesting, sort of just vanished. Now, it would be kind of silly to say that the rate that the radius is growing is equal to the rate that the volume is growing. Why would that be kind of silly? The rate that the radius is growing. Because the radius is getting bigger, doesn't that mean the volume is getting bigger? But think about it, the rate of the radius would have to be a linear rate. The radius is growing by 3 inches per second, just to say. The volume's growing by 3 inches per second. Now again, you don't have to be like a genius to realize that volume, just in its essence, is a whole different kind of measurement. It's a cubic measurement. So to say that the radius rate is the same as the volume rate, just on that level, wouldn't make sense. But they're related. They're related. Okay, and the way that they're related is very, very interesting. It's by calculus, which is derivatives, but they're related. And so what we can say is that the rate, or I should say the radius rate, is related to the volume rate. How? Well, again, with calculus, and interestingly, with that formula that I said verbally, the volume formula, it's 4/3 pi r cubed. But you'll find out when we do the derivative of that formula that we will be able to answer a question like this. Now, I'll share with you, we're going to be, once again, looking at like some word problems. This is the only one that I have up on the screen. I actually hand you a nice little paper, but it's probably not a bad idea to still have some of the important parts of this problem, especially it's the first one that we're doing. We're trying to find a volume rate. It's supposed to be kind of highlighted here. It's underlined, so we're trying to find a volume rate. Notice that I'm giving you some radius rates. Actually, the radius rate is that it's growing by, I guess I use centimeters, by 3 centimeters per second. And notice I'm also giving you a statement about the actual size of the radius. Okay, now, before we sink into this, it's a neat problem. Make sure that you get the gist that the radius rate is connected to the volume rate. It's related to it. They're not the same, but they're related, and they're related through some calculus. They're also related through a formula that involves volume and radius. And again, it's the formula for the volume of a sphere. It's 4/3 pi r cubed. I don't want you to right away get too worried about the formula. We're trying to learn calculus. If you need formulas, we'll figure that out. But that is the geometry formula for the volume of a sphere. And you probably, at least it sounds somewhat familiar. Well, I'm going to show you a new way to do the derivative. Okay? Sort of. It's not like all of a sudden the rules change. But what is going to change is the variable that we will do the derivative with respect to. Now that's kind of a mouthful, but let me say it again. What is going to change is the variable that we do the derivative with respect to. And what I'm talking about here is that we will do the derivative with respect to time. Let me show you what that means. For starters, it means that our denominator will become dt. But as you start to learn and understand what this means more, you'll realize that that means that we're doing this with respect to time. Now, if you're like, what do you mean respect to time? Is it like Aretha Franklin, R-E-S-P-E-C-T? You know, she wants some respect. It means more of what is the variable? What is the variable that has a derivative of 1? Now, that used to be the letter x, right? If you did the derivative of x, it was 1. Okay, and that was kind of like whenever we did a problem, it was basically something to do with x. But now, the variable that has basically a derivative that we know is the variable t. Now you say, but there's no t in here. You're exactly right. We're like now adapting the way to do a derivative. We're allowing this variable to become the new variable. Okay, now I'm not going to keep going around in circles with that, except that you will start to realize that when time gets in the problem, check this out. We have the change in volume over the change in time. And what that means is we have a rate. This is important. I hope you're like really thinking right now, because maybe it's one of the more important things this whole lesson, that you realize that the change in volume over the change in time, we now have a rate, because rates are always per time. Rates are always per time. Okay, so you're going to discover that we're transforming this equation into a rate equation. It's really neat, but let's keep transforming it so you can see some more. Okay, 4/3 pi. There's never a bad time to talk about the derivative of that. Well, it's just a coefficient. Okay, I know it looks like it's big and bad or that something should happen, but it's just a coefficient. Coefficients always come along for the ride. So 4/3 pi is still part of my derivative. Now, the r cubed, next kind of major part of this problem, especially the first time through. R cubed. First, it'll be helpful to think of it as a chain rule, r cubed, to think of it as an inside and an outside. Why? Well, if I do the derivative of r cubed with respect to t, I would do the derivative of the outside. I would leave the inside alone. I would finish the derivative of the outside. But then I will do the derivative of the inside. Now, what's the derivative of r? Well, this is the whole idea where I'm trying to help you see that the derivative of r with respect to time is actually just going to be dr dt, which stands for the derivative of r with respect to time. It's funny, it's more like a symbol. But it's a symbol that means something. It means something. Do you realize what it means? I actually have it up on the screen here. DRDT means, oh, I forgot we have Bubble Bob. There was supposed to be like a sound effect of a popping bubbles. It didn't work. So, but let's keep going here. Maybe you already wrote that dVdt is the change in volume over the change in time. dRdt is the same idea. It's the change in the radius over the change in time. It's the rate. It's the radius rate. So, and here's kind of the magic of the lesson. I mean, I like it, and I want you, kids will say that's neat, but here's the magic of the lesson. This formula can be simplified a little bit, right? Let's make sure that, you don't get lost in some of the simple algebras. Divide out the threes. Okay, great. So I get 4 pi r squared dr dt. 4 pi r squared dr dt. One more excuse to blow a bubble. When I ask the question, how is the volume rate? How is it related to the radius rate? The answer is by this. Okay, how is the volume rate related to the radius rate? It's related by multiplying 4 pi times the radius squared times dr dt. That's a formula. It tells you how the volume is related. It tells you how the volume rate is related to the radius rate. What does this mean? Well, it means that it was on that other screen, right? It means that if the radius is 6 centimeters long, like at that moment in time, if I take a snapshot, if the radius is 6 centimeters long, and I'll square it, and at that moment in time, it was growing by 3 centimeters a second. Well, then I'll multiply it. Make sure you realize that 3 centimeters per second represents dr dt. But here's the answer. Here's how the rate of the volume is related to the radius rate. Okay, it's a little formula. It's a little derivative. And obviously a little computation. If you plug it in your calculator, you get 1,357. Now, for the sciencey kid, it's centimeters cubed because it's volume per second. Remember how we said it would be silly to say that the volume would change by the same rate. It would be silly to say that the volume would change by 3 centimeters. In fact, it's quite a bit different. The volume changes by 1,300 centimeters cubed per second. Okay, now problems like this are examples of related rates. They ask us to calculate a rate that we cannot measure from a rate that we can. And to do so, we'll write an equation that relates the variables. We will differentiate with respect to time, and then we'll get an equation that's going to relate what we know with what we already know. With what we want to know with what we already know. Okay, we already knew what the radius rate was, but we used it to determine the volume rate. Okay, and again, that's because we used related rates. All right, well, more good stuff when you guys come back, right?